Ed's absolutely right, of course. There is, besides the cultural analogy, which relates to, in fact, a physical phenomenon within the reality of the world as we know it, as manifested, in fact, in the biophilic physics of that particular plant growth, catastrophe theory and chaos, and in fact the organization of systems chaotically is significant. You can have, and there are in everyday situations, real world situations that are all around us, of which that's a case in point, the growth of the bamboo plant. Critical points in the progress of events at which you can leap by orders of magnitude to results that by all previous appearances, except in faith, were unreal. And in fact then, they can be reality. As Robert Goddard said, to paraphrase him, it is difficult to in fact tell what is impossible because the dreams of yesterday are the hopes of today and the reality of tomorrow. Let's see what some of the dreams of yesterday that are in fact the hopes of many today, they were our hopes yesterday and continue to be just on the edge of reality. And let's see what that reality is going to look like. Let me introduce to you our speaker for this afternoon, Robert Zubrin from Martin Marietta Astro. He's senior engineer there on the Moon and Mars Initiative missions work that Martin Marietta is doing. Robert, come talk to us.
Well, I want to say that it is truly an honor to have been asked to close this conference. I was a little overwhelmed when Charles Miller called me up and asked me to do it, and I'll try to live up to his expectations. The topic that I'm going to talk about, that I was intending to talk about, is the colonization of Mars. But the colonization of Mars has got to be seen as part of basically, or the Moon for that matter, three phases, the way I see it. So you have an exploration phase, a base building phase, and finally a true large-scale colonization phase. And it's clear that you don't get to the third unless you can get through the first two. And we've heard a lot at this conference about really the critical juncture that phase one, that is the initiation of the true exploration of Mars, and the thorough exploration and the beginning of base building on the Moon is represented by SEI, the critical phase that's in, and a somewhat grim predicament because of the opposition in Congress and the appearance that has been generated that SEI is a somewhat unattractive program looking like $400 billion over 40 years, and we don't even get to Mars until the people who are now in grade school are ready to retire. So that, well, at Martin Marietta we have what we call a scenario development team. I'm on it. And we've developed a mission architecture for doing SEI that we believe is much more cost effective than the sorts of things that you've seen up till now. And the particular architecture that I'm going to show you at the beginning of this, and then move from there through a base building phase on Mars to a discussion of the question of colonizing Mars in a very large way. This mission architecture was worked out by me in collaboration with David Baker, a co-worker of mine over there. We call it Mars Direct. It's a little bit misnamed because we're also able to do the Moon with the same hardware, about 80% commonality. And the missions, what you're about to see, is extremely technologically conservative. We have designed it in order to create a mission architecture which we believe can be potentially acceptable to NASA with its imperatives for safety and reliability and assuredness that the thing will really work. And not that it would really be great if it did work, but it won't. Okay. And our philosophy on this is to get the SEI going, get both the Moon and Mars going now, at the same time that more advanced technologies are aggressively pursued, and then those are introduced into the scenario when they become available. But we don't hold the mission hostage to them, but on the other hand, we don't freeze the technology and stay forever at the current state of the art. So I'm going to introduce to you the architecture known as Mars Direct. This is the first fully open presentation of this architecture anywhere. We'll start, I'm going to concentrate on the Mars side of it, and I will briefly discuss how it can be used for the Moon. I think the people here are capable of putting together the missing blanks on that, but I want to keep the focus on Mars, and you'll see how we can do the whole SEI in it, and then move on from there. First slide. This is the basic mission plan to the Mars Direct architecture. What you have is a launch vehicle, which is a shuttle-derived launch vehicle with a substantial hydrogen-oxygen upper stage. That is, what that launch vehicle consists of is 2 SRBs off the shelf, an external tank, except without the ogive, which is the pointy thing on top of the ET today, just get rid of that, and 4 main engines, not 3, it's got to be 4. There are reasons for that, in a pod at the bottom. And then on top of the external tank, a hydrogen-oxygen upper stage with about 250,000 pounds of thrust, which is about half the thrust of an SSME. It's about equal to that of a J2 engine that was used during Apollo. Now, this booster can lift 120 tons, metric tons to LEO, but that's not what it's designed to do. It could do that, and if you want a space station, it can launch it for you in an afternoon. But this thing is designed to send payloads to the Moon and Mars, direct, lift and throw. Keep it simple, the same way we would do a space mission today. This can throw 40 metric tons onto a minimum energy trans-Mars injection trajectory, a little more than that actually, and about 50 metric tons onto trans-lunar injection. Well, what do? At an early launch opportunity, which is really December 96, we call it 97, to work in even numbers here, we lift and throw onto a trajectory to Mars a 40 metric ton payload. There's no one in it. It's unmanned. What this payload consists of is the following. The object that you see up there on the first line. It is a 2-stage methane oxygen driven Mars ascent and Earth return vehicle, unfueled. There's no methane oxygen in it. If it was, it would weigh a lot more than it does. It's got an aero brake and a small amount of hydrogen oxygen and hydrogen oxygen engines to land it on Mars with the aid of a parachute. That's a very small delta V. And it has, within the tanks that are later going to hold the methane and oxygen, 6 tons of liquid hydrogen cargo. And it has a 100 kilowatt, which is a rather small, nuclear reactor, 100 kilowatt electric, mounted in the back of a methane oxygen driven light truck. The reactor doesn't drive the truck, it's just a conventional truck with an oxygen tank. So it can work on Mars. Okay, this thing gets to Mars. It aero captures into orbit at Mars, and then it enters and it lands with the aid of a chute. Now you're on the ground. What do? You telerobotically drive the truck slowly, because there's a time lag in transmission signals from Mars to Earth. You take your time. You drive the truck a couple of 100 yards away from the landing site, and with the help of a winch, you lower the reactor off of the truck into a depression in the terrain, either a natural one or one that you create with a couple of sticks of dynamite. Okay. Then the radiators of the reactor are deployed. A cable has been run back to the ship during this whole process. We're unwinding cable off of the windlass as we drive along. And we have power. The reactor has not been used until this point. The reactor has been clean until it is on the ground on Mars. Now, we got 100 kilowatts at the landing site. What do we do with it? We use it to run a pump. And what we do is we acquire Martian atmosphere, which is 95% carbon dioxide, and which can be easily acquired as a simple physical acquisition process. It can be liquefied through simple compression and then distilled through evaporation in an extremely simple process. We react the carbon dioxide catalytically with the hydrogen to produce methane and water. That is an exothermic reaction. You are running downhill on the chemical slope. And what that means is you can do it fast. The rate that governs how you can do that reaction is governed only by two things. One, the rate at which you can acquire raw CO2, which is fast because it's a simple pump process. And the second is the rate at which you can dissipate the heat generated by the reaction, which is also fast because you're not trying to convert it to electricity. You can just use high temperature radiators and throw it away. Okay. And what it means is that with 100 kilowatts working for you, you can turn all of your 6 tons of liquid hydrogen into methane and water in 25 hours. Okay, if you have half capacity, do it in 2 days. Doesn't matter. 2 days, 3 days, doesn't make any difference. You can do it fast. There is no problem with long-term storage of cryogenic hydrogen on the surface of Mars. You are rapidly fixing the hydrogen into a non-cryogenic form. Now what do? You liquefy the methane as it is produced, and then when you're all done with fixing the hydrogen, you begin a much longer and more tedious process because it's endothermic of electrolysing the water. As the hydrogen is produced, it is run back through the methanation reaction. As the oxygen is produced, it is liquefied and stored as liquid oxygen. Okay? Ultimately, that process produces about 24 tons of methane and about 48 tons of liquid oxygen. So you've already levered 6 tons into 72, but we will actually generate more oxygen through direct reduction of Mars atmospheric CO2 into carbon monoxide and oxygen, and store the oxygen and throw away the monoxide. And ultimately we are going to produce, for our desired mixture ratio that we're going to run our engines at, 107 tons of methane oxygen. The leverage that is done here is 18 to 1. 6 tons of hydrogen delivered produces 107 tons of methane on Mars, and every one of the reactions that we're proposing to use here has been in widespread commercial use for 100 years on Earth. Okay, so now how long does it take to do those 2 other reactions, which you can take a long time on because you don't have a cryogen to work with? If you had the full 100 kilowatts from the reactor, it would take 5 months. But let's say we have half capacity, to be conservative, 10 months. Well, it took 8 months for that ship to fly to Mars. It took 10 months to make the propellant. That's 18 months. Okay? There are 26 months between launch opportunities from Earth to Mars. Only 18 have gone by. That means you've got enough time, plenty of time, to evaluate whether the propellant production operation has been successfully completed, and if it has, in 1999, at the next mission opportunity, you launch 2 more boosters. One sends another Earth return vehicle / fuel factory. The other sends a manned spacecraft, which is a HAB, and that is a simple disc HAB, 27 feet in diameter, with 2 decks, 600 square feet of floor space per deck. You get artificial gravity on the way out to Mars simply by tethering off the burnt-out upper stage and rotating at 1 RPM with a 1,500-meter tether. It's a very low-risk first application of tethers in space because if something goes wrong, you just clip the tether and all you've lost is artificial G. The element is no longer mission critical. Anyway, when you do get to Mars, and actually the manned vehicle is leading the unmanned one out by perhaps a week or 2, it aero captures into orbit. Well, shortly before it aero captures, it dumps the tether, throws away the stage. Then it aero captures into orbit, and then it goes and it lands at landing site number 1, where there is a fully fueled Earth return vehicle waiting for it. Now, we've been on the ground at site number 1 for 2 years. We've had a few local science rovers running around taking pictures. We found the absolute best landing field in that vicinity. We've laid out navigation beacons, radar beacons right on the ground. X marks the spot. We've got a human pilot on board. The thing coming in, we should be able to land right there. Okay. Now, if, however, there is an error, a massive error, and we land 30 miles away, and even both Vikings flying totally blind without any navigation errors or any control once they entered, were able to land within 30 miles. It's not a problem, because that HAB has with it a pressurized ground rover which uses methane oxygen engines. We do everything on the ground with methane oxygen, which has a one-way theoretical range, assuming no chasms block it or something like that, but a one-way capability maximum of 600 miles. It is almost inconceivable you cannot land within the range of that pressurized ground rover. But if you do, If things go wrong, there is a third level of backup in the scenario, which is simply that you have another Earth return vehicle fuel factory following you out. And if you do land 3,000 miles away by accident, you redirect the second one to land by you, and then you make propellant there. Now, in that case, you're counting on the fuel factory to operate in the present tense as opposed to the past tense, but this is a third level backup. Okay? And finally, the fourth level of backup is the fact that all the supplies for the mission are in the HAB, 3-year mission. They can actually tough it out on the ground on Mars until a relief mission could be launched at the next launch opportunity. So there's a 4-layer defense in depth on the mission. It's extremely conservative. Now, let's say, however, you do land correctly at site number 1. Then what you do is you take the second ERV fuel factory and you land it at a new site, which could be anywhere. But let's say, for example, you choose a distance 500 miles away. I like that because that is a long distance away, but within the one-way driving range of your ground transportation. It starts then making methane ox, which it will use to support the next manned expedition, which flies out in 2001, along with another ERV to open up site number 3. And so it goes. So each 2 years, you launch 2 boosters. That is an average rate of launch of 1 per year to support a virtually continuous presence of humanity on Mars. That can be easily integrated into the existing, launch schedules or whatever. You can clearly do it at the same time you are establishing a lunar base or any other objective you want to do. Okay, you are not demanding a monopoly of the space capability of the United States to pursue Mars. You have gotten it down to a scale where it can be pursued in conjunction with multitude of other goals at the same time. Okay, now you're on the ground here. Now, you're going to stay on the ground for 1.5 years until the planets line up correctly for a minimum energy traverse back to Earth. You have immense mobility while you're on the ground because of the 107 tons of methane oxygen that you produced, only 96 are actually needed for the Earth return vehicle. The other 11 tons can be used to support operation by surface vehicles. And with 11 tons of methane oxygen to support ground vehicle operations, you have available to you a total traverse, not range, but traverse, mileage as it were, of about 11,000 miles. 11,000 miles of surface activity, quite a bit different from the 20 miles of a lunar golf cart. Okay? And that's what chemical fuels do for you. That's what indigenous fuels do for you. This is proof of something which I think this society has taken as an axiom for years, which is that the key to space is the utilization of extraterrestrial resources. Okay, and it is realistic to be at Mars for 1.5 years in this scenario because you do not have a mothership. There is nobody floating up in orbit playing Mike Collins for 2 years saying, when are we going home, folks? Okay. Everybody is on the ground. They can be protected by the Mars atmosphere against solar flares. You can put sandbags on the roof of your house, protection against cosmic rays. You've got natural gravity. Okay, you can do it. And furthermore, with everyone on the ground, you maximize the use of your manpower because each man you send to Mars is precious. Each man you send to Mars is an enormous mass hit in terms of the launch cost originally, in terms of what's required to support them. So they're all on the ground where they can do the job of exploring Mars, where they can support each other. You only need 1 doctor for the mission instead of 2, 1 for the mothership and 1 for the ground. You only need 1, and Mr. Fix-It for the, you only need 1 of everything, or if you have 2, you're fully redundant instead of non-redundant. Okay? Any way you slice it, it's better to keep the crew together. Okay? So, we do, instead of having a mission which takes 8 launches, and you get to stay at Mars for 3 weeks, okay, with a small crew, we do it with 2 launches, and you get to stay at Mars for 1.5 years, where you can do a substantial amount of exploration. You've got the mobility, you've got the time, you've got what it takes to do the job. Now, next slide. This shows a depiction of what the Mars landing site would be like, and you can see it's actually a miniature base in and of itself. You've got the HAB, And in our initial missions, we would just deck out the upper deck of the HAB as habitation and use the lower deck as a garage and workspace and cargo area. You've got the Earth return vehicle, the reactor is in that crater in the background, some ground vehicles, and in this case an experimental greenhouse for beginning the experiments on growing crops on the Martian surface. Because you've got the time and you also have the power to do it. You've got a power-rich environment. You've got the reactor, and you also have mobile power with the methane ox engines and the ground cars. You can go to a remote site and you can drill, because you can generate 1,500 kilowatts with an internal combustion engine, no sweat. Okay? You really have a capable mission here. So, when these people leave this site, they leave behind that HAB. They leave behind the greenhouse. They leave the reactor. They leave the fuel factory, which is in kind of the lowest deck of this Earth return vehicle. You can't quite see the stage brake. And the ground vehicles, of course, are left behind. So we're leaving behind a miniature base in place at a given site. Now, we've got a choice. We could go back to this site. We could build it up as a large base. Or we can open up new bases. The approach is completely modular. But next slide. This illustrates the mission strategy. Send Texas to Mars. Each of those circles that you see there has a radius of 300 miles, and their centers are separated by 500 miles. And in other words, if the vehicle has a one-way range of 600 miles, it has a sortie range from a given point of 300. Okay? So, but once a second site is established, you don't have to use the full 11 tons of methane ox you produce at a given site. Let's say you use 9. You leave 2 there. So that when people come driving over from site number 2 to revisit site number 1, they can live in the HAB and they can refuel there and continue to explore in that area. So what you're doing is you're opening up human territory on Mars on a very large scale. Each 2 years, you're opening up a new area approximately the size of the state of Texas. Okay? So that's your exploration strategy, constantly opening up new territory, satisfying the science imperative. With the time and mobility that we have, we'll almost certainly be able to discover water and experiment and find ways to extract it from the Martian permafrost, which means that at that point we don't have to haul liquid hydrogen to Mars anymore. That will give us additional leverage, or we can continue to produce propellant for ground vehicles at any amount at that point, and so forth. We bring the liquid hydrogen in the early missions because it just cuts short all the nonsense about what if you don't find water. You say you don't need to find water. Okay? It's nice if you find it, but you don't need to find it. You can do without the beginning until we get going. Now, clearly, as I say, this approach is modular. At a certain point, you won't want to continue opening up new sites necessarily. You might want to start concentrating landing bases at a given site. In other words, you land 4, 5, 6 HABs at a given location. Maybe some of them are 2-deck complete habitations on both decks. Maybe some of them have no habitation in it and just filled to the gills with cargo. Any way you slice it, you can have a grand base with 10 HABs, or you can have a lot of medium-sized ones with 3 each, or you can do it any way you like. It's totally flexible. Next slide. Now here's where I'm going to briefly allude to the lunar commonality that's implicit in this scenario. Here's the entire SEI. You've got one launch vehicle that does both the Moon and Mars. We've explained how you do Mars missions with this architecture. The way you do Moon missions with this architecture is extremely simple. First, you launch a HAB at Mars. Obviously, you get rid of the aero brake. It doesn't do you any good at the Moon. Okay? You throw the HAB at the Moon. Instead of the aero brake, it has larger tanks for its hydrogen-oxygen engines. That's all. Which have to be, well, delta V is larger and all that. But even so, we can handle it. We have a larger throw capability to the Moon with this booster. We land the HAB direct on the Moon with no one in it. Or 2, or 3, however many you want to open up a given site on the Moon. But let's go with a minimal mission to start. You throw one of these things to the Moon, and now you've got a house sitting on the Moon. Then what you do is you take one of the methane ox Earth return vehicles, except you get rid of the lower stage. The reason why we designed that vehicle so that with the lower stage, it can send you back to Earth orbit from the Martian surface, with the 2 stages, or if you get rid of the lower stage and just use the upper stage, you've got the thrust and you've got the delta V necessary to send you back to Earth orbit from the Mars surface, from the Moon surface. So this thing is flown to the Moon initially fully fueled with methane ox. You can do it because the weight of the propellant in the upper stage isn't that great. And you just land it on the Moon next to the HAB. You walk out of this, you go and live in the HAB. You stay on the moon for as long as you like, and then when you're done, you walk out of the hab, get into the Earthly vehicle, and go home. It's that simple. And you can establish moon bases in the same modular way, big bases, little bases, scattered bases, together bases, any way you like. Methane oxygen obviously costs you a little something. It's not quite as high a performing propellant as hydrogen oxygen is. You only get about 370 seconds of specific impulse compared to maybe 450 with hydrogen oxygen. But you don't have the problem of long-term storage of a very hard cryogen on the lunar surface. And that's a tremendous advantage for these missions because we want to stay on the lunar surface a long time. And that... And since all the heavy cargo being delivered by rocket is going one way to the moon, when the time comes to deliver heavy cargoes off the moon, you know, for construction in space and so forth, we can use mass drivers or whatever for that. All that has to go home from the moon by rocket is people. And those payloads are small. And so we can take the hit on using methane ox. And we've got a very simple architecture. You don't have to rendezvous with a lunar excursion vehicle. It's a problem. Lunar orbital rendezvous was great for Apollo because it lightened the mission. But it's a problem because lunar orbits are unstable. And if you're only staying at the moon for a short amount of time like Apollo did, that's okay. You can have a guy in there, the orbit doesn't change that much over 2-3 days a week, okay, and you rendezvous and go home. But if you're going to stay on the moon an indefinite period, clearly you don't want anyone hanging around in orbit waiting for you to leave, okay? And you don't really want to have a ship that's without anyone in it hanging around in orbit waiting for you to leave. And if you leave it at the space station and say, we want to leave the moon now, come and get us, there's an emergency here, they say, sure, we'll launch a couple of shuttle Cs and an STS and put it together and be right over. You know, that doesn't do the job. This is much simpler. You have the means available on the moon to go home at any time. And once lunar oxygen is available, methane oxygen engines can use it, and the difference then in the payload deliverable with the manned vehicle to the moon with hydrogen oxygen or methane oxygen under those conditions is too small to matter. So it's a very simple architecture for doing the moon or Mars with the same components. And I want to say one thing about that. Look, obviously this is appealing from the point of view that it makes the whole thing much less costly. We don't have special vehicles, LEVs, LTVs, MEVs, MTVs, rendezvousing with each other. Going here and there and everywhere, okay? We don't need any on-orbit assembly, none. We don't have to augment the space station with a dual keel, okay? We just lift and throw. We don't have to do 12 impossible things. And because the hardware is common to the varied objectives of the Space Exploration Initiative, I mean, face it, look, you take this side here. We've got Mars advocates, we've got Moon advocates, we've got L5 advocates, we've got all kinds of people, but we're not going to have enough political strength to make this program happen unless we all support it. So it's got to be a balanced program that doesn't shut anybody out. And this can do it. So now, I've talked now about how we can get SEI off the ground. Because, I mean, look, you look at this, I defy anybody to tell me with a straight face that this is a $400 billion program here. It ain't. So, the reason why I wanted to show all this stuff to you was because you're the space activists, and I wanted each and every one of you to know when you left this place that it is absolutely untrue that SEI is a hopeless bog of $400 billion in 40 or 50 years and all the rest. It ain't so. This really can be done. Okay? And we're going to get that message out. Now, I want to talk now about... What?
Get it to Congress.
Yeah, well, we're going to.
One question.
Well, I'll take a brief question, but then I want to go on.
Brief question concerning the $400 billion. What level is it?
I don't know. People... costing to me is a black art, all right?
Right.
But people have looked at this, and I've got estimates by people looking at this ranging between $20 and $100 billion.
Okay. That's
Okay.
the figure I wanted.
Okay, so you can pick a number. Maybe it's 100, maybe it's 20, maybe it's 50, but it's not 400.
Right.
And by 100, that 100 is not for the first mission. That 100 is for 20 years, including maybe 5, 6, 8 missions where you already have established a fairly substantial presence on both the Moon and Mars in this way. Okay, that's to really get the thing underway. Obviously, as t goes to infinity, cost goes to infinity. But but within the event horizon, you know, that you choose, it's not that large a cost. Okay, now what I want to talk about is how we can start moving this thing towards, briefly, I'll talk through the Phase 2 base building program with regard to Mars, and then I'm going to talk about colonization. And I'll start introducing some new technologies. Up to now, we've been very technically conservative, because that's what we have to be in order to get it going. But now let's go with some things that can come along. Okay, most of you, I think, are familiar with this. This is a nuclear thermal rocket engine. It was called NERVA. 20 of these were built in this country during the 1960s and early 70s. 20 were built and tested. And while there were some problems at the beginning of the program, towards the end of the program, the things worked like a charm. Now, these engines work by taking liquid hydrogen and running them through the nuclear reactor, which is just a heat source, which heats it to high temperature vapor and exhausts it out a rocket nozzle. It is a flying steam kettle. The physical principle underlying it is totally trivial. Okay? These things were built, they were tested. Next slide. Okay. How many remember 1968? Okay. Well, while the legions of Eugene McCarthy were tramping through their historic trek through the snows of New Hampshire, this was going on in Nevada. This is the test of the NRX A6. This test lasted 62 minutes, generated 50,000 pounds of thrust for, as I said, 62 minutes with a specific impulse of about 850 seconds. This level of performance for this length of time would have been is completely sufficient to do an entire manned-Mars mission with this engine. Okay, with about half the mass in LEO of doing it with chemical propulsion. The NERVA engines made it through what NASA calls technology level 6, which is through ground testing. The next step in the program would have been a flight test. And they were baselined by Wernher von Braun and NASA at that time to be the engine of choice for the manned Mars mission, which was supposed to follow Apollo in 1981. Okay? But the Nixon administration, in its infinite wisdom, decided that it had had enough of a program that it hadn't invented. And, of course, as you know, they canceled the Saturn V and they canceled NERVA. There was no technical problem with NERVA any more than there was a technical problem with the Saturn V. It just represented an embarrassing excess of capability. Now, okay, but we can redevelop NERVA. Some of the old cans are still around. Westinghouse Company has preserved all the specs on it. We have all the information. The blueprints on this one was not burned. Okay? And this can give us much greater throw to Mars. With a modification of the booster that I showed you, basically increasing the thrust on the upper stage and adding a third stage NERVA, we can throw 80 tons to Mars with a single launch instead of 40. It's a factor of 2 benefit. That's pretty good. We can do a single direct Mars mission in 1 launch instead of 2. Okay. But you can do other things with these things. And this is a little concept that I'm responsible for. Next slide. This is called a nymph, which has pleased the Public Relations Department of Martin Marietta. The concept here, see, the NERVA program was geared towards using nuclear thermal engines for their high performance, 900 second specific impulse, twice that of chemical fuels. That's good, that's important, that'll give you this factor 2 leverage that I've mentioned. But there's another advantage to these engines, which is that fundamentally the technology is versatile. Fundamentally you can use it in principle and get some level of performance or other out of almost any volatile substance. Water, nitrogen, methane, CO2. Mars has a CO2 atmosphere. So we have a landing vehicle here, the nymph. It comes down, it lands on Mars, maybe with the help of a chute, just enough propellant to put it down on the ground after the parachute-assisted landing. Then what you do is you run a pump. You compress CO2 out of the Martian atmosphere, and at the temperatures that exist on Mars, CO2 will liquefy under about 100 pounds per square inch pressure. It is an extremely simple physical acquisition process. The advantage of it over producing chemical fuels is that it takes about 1/100th as much energy to produce a given mass of fuel this way as it does to perform a chemical synthesis operation. So what you've got here is a very small amount of power required to produce an enormous amount of propellant in a very short amount of time, such that the nymph, with a 25 kilowatt power source, which could come off of its reactor, which could come off of a dynamic isotope power source, or could come off of a solar array that is deployed by hand by the crew, walking outside. Any way you slice it, with 25 kW, this can acquire enough propellant to send it back up to orbit around Mars in 30 days. Or, what is actually more valuable, to hop from one point on Mars to virtually any other point on Mars in a single hop in 15 to 20 days of propellant acquisition. At which point you can land again and then refuel again. So you have unlimited mobility. This vehicle gives you global mobility on Mars, and therefore it multiplies the science capability at Mars. Astronauts can visit 10 sites instead of one within a given mission duration. Okay? And to my way of thinking, the addition of this vehicle to the mission architecture at that point enables you to go from opening up new sites to concentrating on developing a single site, because you are no longer in conflict with the exploration imperative. You can build up a single site and satisfy the exploration by having scientists set forth in the NIP and visit any number of sites they want, while we develop resource utilization and processing and that kind of thing at a given site where most of the landings are now concentrated. And of course, which given site that is will be decided on the basis of knowledge that has been generated by the fact that we've explored a large area in the previous spread out landing pattern. Next slide. Well, this is just to illustrate that there are various propellants that could be used in a nuclear thermal rocket. Now, the number that counts is 2800 Kelvin. That's a realistic temperature for one of these engines. And as you can see, carbon dioxide only yields 280 seconds of specific impulse at that temperature. It's not great, but it is good enough to get you back to orbit or to hop around Mars, and that's what matters. Now, if you want higher performance, water or methane will do it, okay? But they're harder to get. To get water on Mars, you're going to have to break down permafrost or at least ice at the poles. So it's a harder process. Methane, you have to actually manufacture with chemical synthesis, though as you can see, it's a super propellant, it's 600 seconds. However, as we'll discuss briefly, while these may be a little hard to come by on Mars, they are not that hard to come by in certain other places in the solar system. And thus, this type of propulsion system, while we would gear it towards CO2 at Mars, we could use it elsewhere in the solar system with other propellants to achieve missions, particularly in the outer solar system. Yes. Next. Here's the artist's conception of a NIMP vehicle. The top is the control deck. That's where the people are when the reactor's fired. Then we have an additional deck of habitation. Then you've got the pumps, which would really be a lot smaller than that, because with 25 kilowatts of pumping power, I mean, that's like a 30 horsepower pump. Okay? And so it's smaller than that. But then you have the big main propellant tank where the CO2 is stored. And then you've got the reactor, and not seen above the reactor is a dish shield. And around the reactor is a coaxial tank, which is also filled with CO2. And the way this works is, you see, when the reactor is being fired, the people are shielded from it by the dish shield, by the enormous mass of propellant in the main tank, by the machinery, by the distance, and by a second shield which sits just under their butts on the control deck. Okay. When you land on the ground, before you leave, you fill up the coaxial tank with liquid CO2 and at least some of the main tank, and thus you're surrounding the reactor with a very thick shield of liquid CO2 so as to facilitate ground operations within the vicinity of the building. The NIMP reactor is radioactive, of course, after it's been fired, but not terribly so because the burn times are very short. It's about 2 orders of magnitude less radioactive in long-term radionuclides than an RTG. Okay. So, it's not too bad. It's a workable thing. Next slide.
What about nuclear exhaust?
The fuel particles themselves are enclosed within non-fissile material. There is a certain amount of fission products that can migrate through solid material, but those are all noble gases like xenon and krypton, and they blow away with the wind. They can't contaminate anything. And once the reactor is shut down, they are no longer emitted. So it's a very marginal problem. What? The carbon has an extremely small activation cross-section from neutrons. Okay. Anyway, okay, if you have a nymph and you've got an NTR, that's your third stage NTR up there, you can do a manned-Mars mission in a single launch. The nymph can't quite leap back to Earth from the Martian surface, so it leaves in orbit a small methane-oxygen stage, and it rendezvous with that, and that kicks it home. But really, the important thing about the nymph is not to do a manned Mars mission in a single launch with it, but just send a couple of them to Mars and have them to use at Mars for exploration and for something else. Next slide. Oh, this is just another nymph concept. This is obviously a winged aircraft which takes off like a Harrier by piping hot gas to the ventral nozzles, and then when it is off the ground, it pipes hot gas to the rear nozzle and it goes scooting away. And the reason why the wings are so small for a Martian airplane is because it flies at Mach 4. And which you can do because you've got the power of a nuclear thermal rocket engine. And this can fly, level flight at Mach 4 at low altitude, or it can achieve low Mars orbit. Next slide. You might ask, why use a nymph for global mobility instead of indigenous chemical fuel? One answer is because the chemical fuel is 100 times more expensive from an energy point of view. But the other answer is this. Because the chemical fuel must be produced at a fixed site, a vehicle using it for exploration has to do 2 delta Vs, one to leave the site and land, and the other to leave that and come and land back at the base. Whereas the nymph only has to do a one-way hop. So what it means is that the delta Vs for the chemical vehicle double, and very quickly, the mass ratio of the vehicle, as the hop rate increases, becomes larger than that which is really achievable from an engineering point of view. Whereas the nymph can easily attain Mars orbit and then come in and land anywhere, so it has complete global mobility. A chemical hopper would only have a realistic range of about 1,000 or 1,300 kilometers or so, whereas the nymph has total mobility. Next. But it can do something else. It can transport cargo, and this is very important when you start talking about building bases on Mars. It can achieve Mars orbit if it's not carrying a lot, but how much can it achieve in point-to-point transportation, which is a smaller delta V, if you start loading cargo on? Well, if it's got 40 tons of cargo, it can travel 4,000 kilometers, which is roughly the distance from the pole to the equator on Mars. Which means you go to the Martian pole, stock up on water easily acquired, and bring it back to your base near the equator, no sweat. And you don't need any infrastructure at either end of the flight path. You can even take 100 tons, 1,000 kilometers. You can drop cargoes off here and there. You have mobility, you've got transport capability on the surface. Next slide. Oh, well this is just, point that up, that's a rocket, you know, it should go up. Especially since it's one of ours, that's a Titan IV. This is to illustrate an early possible use of the nymph. That's a Titan IV with a Centaur, and up above it is a miniature unmanned nymph which can be used for a Mars rover sample return mission, except that instead of visiting one site like Mars rover sample return does, it can visit 10 or 20. So it has a vastly larger science return, and here your shielding problems go away completely because it's unmanned. And in this case, the way it returns the samples to Earth, next slide, is with those 2 little space torpedoes there. Those are Star 24 solid rocket engines and Discover type capsules, and basically you collect samples, you load it into one of those capsules, and then the nymph descends to low Mars orbit and shoots one of those back to Earth with the nymph staying in Mars orbit. Then the capsules get to Earth, they land like Apollo capsules, the Russian trawlers pick them up. The Russian scientists examine our samples, and they tell us, look, sites 3 and 8 were really the ones you want to look at. And we say, right, and we send the nymph back down. It collects a comprehensive set of samples from the 2 or 3 most interesting sites. Then it goes back up to orbit, and at the next launch opportunity, it sends the second capsule back to Earth, and we get those. Because we caught on. But anyway, this illustrates the mission. 1 Titan IV, visit at least 10 sites, 2 sample shipments allowing feedback in the loop, and returning to Earth 220 kilograms of sample. That's 45 times as much by weight as the current Mars rover sample return mission postulates, and doing it from a multitude of sites and proving out the nymph technology in an unmanned mode as a technology demonstration. Next. All right, I mentioned that we can do this to other places in the solar system. There are ice on the asteroids, water ice on Ceres and on the Trojan asteroids, and on Ganymede, Callisto, Europa. and maybe even on Io, and on the moons of Saturn. And of course, we got methane on Titan. And to me, Titan's a very interesting place. After Mars, it's the most interesting place in the solar system. Next slide. So here's a Titan Explorer mission. This thing is launched to Leo on a Titan 4 or even a space shuttle. It's got a Nerva-type engine, hydrogen in the tank. That propels it out on trans-Saturn injection. It gets to Titan. It spreads open those fold-out wings. Well, it aero captures first to lose its velocity, and then it spreads out its fold-out wings. And you see, Titan has got 1/7 Earth's gravity, but 4 times our atmospheric density. Okay? This thing could travel at 100, this weighs 8 tons dry. It could travel at 100 miles an hour airspeed in Titan's atmosphere and remain airborne with wings of 4 square meters. Okay? With this, I mean, on Titan, you could strap wings on your arms and fly like a bird. Okay, you know, just like in the Robert Heinlein story. You could do it, no question about it. And this vehicle with wings, as you see them sized here, can putt along at 25 miles an hour in Titan's atmosphere and remain airborne. Next slide. So here's the mission. You see, this is an air breather that just intakes air as it flies, heats it in the reactor, and uses that to generate jet thrust. It does a low-level aerial reconnaissance of Titan. We can't image Titan's surface from space because it's all clouded over. So we do a low-level aerial recon. We never land because Titan's got lots of organic chemicals on its surface. It may be sticky. So what we do is we collect samples with little small, this is an unmanned mission, but even smaller drones. These are like little battery-powered tilt-rotor seaplanes. And they can land on either the land or the methane ocean and collect samples and then fly back up to the nymph with them and have their batteries recharged there, and then set forth again. And you have maybe 20 of those little things on board, so if you lose a few, that's the brakes. But anyway, you do a total reconnaissance of the world, you collect samples and pictures from all over, and then when you're done, you gas up with methane from Titan's atmosphere, and you could either go straight back to Earth, or you could go and visit almost any of the other moons of Saturn except for Mimas, land there, collect a sample there, go back to Titan and refuel and do the other moons in succession. So you could do a grand tour, sample collection mission from almost the entire Saturn satellite system and then go back to Earth. And Titan is ultimately a home for people. You've got methane, you've got the atmosphere is actually 90% nitrogen, which is the only other planet in the solar system that has a nitrogen atmosphere. You've got water ice on the surface, you've got what you need, you go to Titan with a reactor, you convert heat there to electricity at 80% efficiency because of the low temperature heat sink. Titan is a target for colonization following Mars, but more on that anon. Now, okay, if we were to talk now, we talked about going to Mars, about exploring Mars, but you say if you're really going to do a colonization effort on Mars, somehow it has to pay for itself. Okay? People can imagine ways that lunar bases, for example, can pay for themselves. We all know those. But how could a Mars colony pay for itself? Clearly, exploration we can afford just to spend and do it because it's a good thing to do. But if you're going to send thousands and millions of people to Mars, even though you're not going there to make money, people don't do things to make money. People make money to do things. Okay? But nevertheless, they have to make money in order to do them. Okay? Now, what I've showed you in terms of system architectures shows the path to possibly a way to commercially support the colonization of Mars. The reason is this. You've all heard, those that you were around in the 60s, heard 10 million times the following sentence in newspapers. If there were diamonds lying on the surface of the moon, it would not pay to send astronauts there to scoop them up because it costs too much to go to the moon. Okay? Now, you all know that if there were diamonds lying on the surface of the moon, it would certainly pay to go there, not to scoop them up with Apollo missions, but you could set up a mass driver on the moon and shoot them home and make a great deal of money. Okay? Okay? No problem at all. And certainly many things a lot less valuable than diamonds from the moon could be sent back that way. But how do you do it from Mars? It's simple. You use the indigenous propellant. You use a nymph, an unmanned nymph, but a large one, a cargo nymph, if you will, that can lift payloads from the Mars surface to low Mars orbit. And then what you do is you shoot those payloads back to Earth with a small methane oxygen engine and an aero capture module on board. So nothing nuclear is coming back to Earth. It's just a chemical unit with an aerobrake. Okay? It only needs to be a very small engine, which even could be manufactured on Earth because it's a high-tech item. Because it's just a second stage. You have a very, well, fairly low thrust, and it can shoot back. Okay? Just to give you an idea, okay, if the NIF can lift 50 tons to, which is 100,000 pounds, to low Mars orbit, about 40,000 of that is payload. Now, to leave an orbital situation and go on to trans-Earth injection, you want a thrust weight of about 0.2. Okay? Now, instead of about 1.5 to leave from a surface. Okay? Now, the object leaving Mars orbit, it only weighs 40,000 pounds in Mars gravity. Okay? 1/8 of that, 1/5 of that 0.2 thrust to weight is 8,000 pounds. You need 8,000 pounds of thrust to send back to Earth a 40,000 pound payload. A chemical engine typically has a thrust to weight of perhaps 40, which means the engine that you need to ship to Mars to move 40,000 pounds back to Earth would only weigh 200 pounds. So you could ship those things to Mars by the crate and send very large payloads back to Earth. Okay? And under those conditions, there are quite a few substances which are worth picking up on Mars and shooting back to Earth. Now, we don't know whether they're available, but Mars is a world. It has as much surface area as the Earth. It's had active geology for about the first 1 billion or 2 years of its existence. Ore-forming processes have occurred on Mars. There's every reason to believe there's all the different kinds of ore on Mars that there are on Earth, though admittedly they have not yet been found. But from the standpoint of geology, there's no reason to believe they're not there. And furthermore, since we know that at one time on the surface of the Earth there were various valuable ores so abundant that primitive societies could pick them up, you know, Aztecs and Incas and ancient Egyptians picking up gold, which you can obviously see was gold, you know, and so forth. So it could be that there are mineral resources on Mars that are plentiful and obvious in ways that is no longer the case on Earth because of the fact that we've been doing things here for too long. Next. So this graph shows you approximately what the balance is for a variety of valuable materials. Now, the break-even point for your Mars operation is that horizontal line, and this is a log-log scale. If you, if it's 10, it means they are actually selling to Earth materials whose value is 10 times as much cash as they would require to support the operation at Mars. And of course, there's a considerable uncertainty because the prices of these materials vary. And there's also an uncertainty relative to how much of the material that is shipped to Mars, what percent of it can be used to support exports. That's what U is. If U is 0.1, that means that 1/10 of the material sent to Mars is supporting the exports. The other 90% is supporting the Martians and enabling them to do what they want to do, to build houses, to increase their standard of living, to expand their habitations. Okay? So if U is 0.1, take a look at that second line there. You can see that if you've got materials that are roughly as valuable as silver or more, and there are many such materials, they could potentially be economically exploited at Mars. Next slide. Now, this here, this was in Ad Astra. This is the Mayflower. This thing is a Mars colonization ship. Okay? This thing is geared towards sending people one way to Mars. Because colonization is a one-way trip, and colonists are people willing to go one way. Okay? And, you know, so that's that. Now, the way this works, as you can see, this is a derivation of our earlier Mars Direct booster. It's got 4 main engines on the bottom. It's got 500,000 pounds of thrust upstairs on the chemical upper stage. But then it has an NTR stage, which is that one up there, and it can then throw those 2 habitations onto, they each weigh 40 tons, onto one-way trajectories to Mars. Each of those things have a 33-foot diameter. There's about 1,800 square feet of floor space on those, not counting what's in the upper deck, which is a cargo attic. But after the cargo is unloaded on Mars, the kids can live there. Anyway, those things are thrown onto direct trans-Mars injection. They tether off of each other, because we don't want to hang around a nuclear reactor. And they spin up. You got artificial G on the way to Mars, and when they get to Mars, they aero capture and they land. Okay? And they provide initial housing for the people that go out in them and the beginnings of their families. Now, okay, there are 6 people can exist on each of these decks, so there's 24 people going to Mars one way with this vehicle. Now let's say starting in the year 2010, just to pick a date, the Earth decides to send 4 of these to Mars per year. It would really be 8 every other year because of the way the launch opportunities to Mars work, but an average of 4 a year. Now, that could be all 4 from the US, because we can afford 4 launches a year to colonize Mars if we want to do that. Or it could be 1 each from us, the Europeans, the Japanese, and what's left of the Soviet Union. Okay. Or any combination thereof. But if you did that, and then you make certain reasonable demographic assumptions about birth rates and death rates and so forth, which I won't bother you with right now, you can compute the population growth curve. Next slide. Oh, well, that shows the halves closer up. Next slide. Right. Now, this, by the way, was based on the assumption that the colonists that go out are all between the ages of 20 and 40, and 50-50 men and women. Okay? It should be self-evident that Chuck Yeager is wrong about not needing female astronauts if you want to colonize Mars. Incidentally, if you want to know the reason why you speak English, it's because the British sent women to America and the French didn't. That's true, that's a fact. That's why when the battle came out in the 1750s, there were about 2 million English-speaking people in North America and only 50,000 French. Anyway. Okay, so Mars needs women. So here's the population growth curve, and you can see we've broken it down. And let's take a point here of 40 years into the colonization effort. You've got 11,000 people on Mars, and about 1/3 of them are native-born Martians, children between the ages of 0 and 19. And you can go on out, and by the year 100 years after the beginning, you've got 80,000 people on Mars. Next slide. And here, we also had this one in Ad Astra. This shows the rate of sustainable colonization on Mars with really, I mean, look, this is totally conservative. We're talking about 4 launches a year with technology frozen at late 20th century levels forever, okay? Okay, this is what you're looking at. You're talking about a rate of colonizing Mars completely comparable to the rate of population growth in colonial America in the 1600s. That is to say, from the point of view of transportation, there is no greater difficulty in colonizing Mars in the immediate future, than there was in colonizing the North America in the 1600s. It is this problem of the same level of difficulty. It can be done. It's not easy, but it can be done. It is a realistic goal for humanity in the coming century. In fact, I would say it's our obligation. Okay? Next slide. Here's this quote. Okay, you know, this is a quote that I lifted from Bradford's book. Bradford was the leader of the Pilgrims. And when the Pilgrims were in Holland and they didn't like the way things were going. They were being assimilated. They were losing their cultural identity. They were losing that which really, in their view, composed their soul. And someone advanced the idea, look, let's go to America. Okay, let's move our entire group to America where we can make our own world, where we can make our own civilization. And this is what he reports. He says, this proposition, being made public and coming to the scanning of all, it raised many variable opinions amongst men and caused many fears and doubts amongst themselves. Some, from their reasons and hopes conceived, labored to stir up and encourage the rest to undertake and prosecute the same. Others, again, out of their fears, objected against it and sought to divert from it, alleging many things, and those neither unreasonable nor unprobable, as that it was a great design, and subject to many unconceivable perils and dangers. It was answered that all great and honorable actions are accompanied with great difficulties, and must be both enterprised and overcome with answerable courages. I think that's great. And that's our heritage. I mean, we celebrate that every year at Thanksgiving. That is what we really celebrate, okay? The moxie that built this country, okay? That was required to build it, that's going to be required to build a civilization on Mars, in which I believe we have. They went to the New World not to make money, folks. Okay, they went there to cut their own path, and I think that that's fundamental. I'll tell you something to digress a small amount. Okay, I recently been reading a book by Václav Havel. He is the playwright who is now the president of Czechoslovakia. A year ago he was in prison. And he wrote in his book, he wrote this in prison, he said, look, the principle of entropy is the principle of reduction of all things to the most probable state, a common state, a uniform state. It's fundamentally the principle of death. Okay? It's the principle that the communist authorities are trying to impose as the basis for society. Okay? The principle of life is the principle of diversity, the principle of evolving to ever more improbable states, to ever more diverse. Okay? It's a negentropic principle. And that's what life seeks, and that's what's fundamental for life. And while it may seem that this principle of uniformity is so much more powerful than the small elements here and there that are struggling for diversity, that are struggling to establish their own identity, it's untrue. Because they are what is alive. And you know, just as a piece of grass can break through the pavement, because it's big, but it's passive, it's nothing, it's dead. That's what's alive, and that's what's real, and that's what's going to happen. Okay? Now, if you look at human society, see, why do we have to go to Mars? I mean, here I've shown you how we can go to Mars, how a Mars civilization can support itself, how it can attain sizable dimensions within a reasonable period of time. And I haven't even mentioned terraforming, which is also a possibility for Mars. Because Mars was once a warm, wet planet and can be so again. Where plants can grow in the open and the slopes of the Olympus Mons can be covered with Colorado pine. It's not so far off as you might think. It's this. It's that living systems, in order to remain diverse, must constantly break out of their existing habitats and find new ones. And in fact, they must always go to the new habitats precisely because they are difficult to go to. They must always colonize a new habitat which they can just marginally make it to. Because there's a tremendous driver there, a tremendous economic incentive to develop transportation technologies that vastly supersede that which we now have. Fusion propulsion, reduce the trip time to Titan to 6 months instead of 4 years, or 4 months, whatever, okay? And when you do that, though, okay, then you say you're opening up Titan to a flood of impossible tourists, okay? You know, snapping pictures and doing other things. Okay, but you've done something else, however. You created the transportation technology for the next step. And a fusion rocket that gives you routine access to Titan gives you a marginal capability for an interstellar mission in 20 to 40-year kinds of time frames. Okay? And there'll be people that will have the stomach for that. And that, in turn, will create the driver for a still next level of transportation technology, which I can't even postulate at the moment, but which I am certain will follow, okay, by exactly the same logic that it has always followed. That Columbus made the voyage across the Atlantic in ships that were so barely capable of it, no one in their right mind would attempt it. He did it. But as soon as they found there was something worth going to across that ocean, the art of naval architecture advanced until it became routine. And so it goes. So, I want to conclude with a quote that goes back a little bit further in time than William Bradford. Okay? Now, as a boy, I used to read a lot of classical history. And there was one favorite speech of mine that Pericles, Athenian statesman, gave. At the end, he gave to the Athenian war dead at the end of the second year of the Peloponnesian War, at Athens' desperate war with the Spartans, the militaristic Spartans and their Peloponnesian allies. And he said, look, okay, these men died, and some of you are their relatives and you're sad, but what did they die for? What did they fight for? Okay, they fought for Athens, and what's Athens all about? Athens here is a city, it is unique, it is a city that has fostered the human quality, the diversity of human beings, the development of their intellects, the flowering of their intellects, a city which has created philosophers who have established a proposition that the human mind is capable of understanding the laws of the universe. A radical, incredible proposition, which is the basis of all science ever since. Okay, and this is what has amazed the world. And he says, future ages will wonder at us, even as the present age wonders at us now. Now, Athens lost the war. Spartans won. But he was right anyway, because it's 2,000 years and people still wonder at Athens. And what I'm saying is that if we do our job right, if we get this SEI going, if we open up the moon, if we colonize Mars, if we go to Titan, and the steps to do, this is the decisive year right now, and maybe the 1 or 2 years that follow to get this thing going. If we do this, then 2,000 years from now, human civilizations that will exist on hundreds of Earth-like planets scattered within this neighborhood of the galaxy will look back on this time and they will wonder at us. Thanks.
I think we can take a little time for a few questions.
In the back.
You've got a great idea. It's fabulous. Permanent presence throughout the solar system. You've also come up with an interesting way of getting rid of a lot of cold work fissionable materials. I think that's great. You're reaching this wire, however, and Satan is waiting for you inside the Beltway with a fly swatter. With the passion of this presentation is incredible. Are you guys working on some way of getting you through to George Bush and Q to present this thing and see if you can punch it through the bureaucracy? And how can we help you do that?
Well, okay, let me... That's a very good question. Are there any other questions? No, I'll tell you what we're doing. Okay, look, we're starting with the Mars Direct stuff, starting with the simplified architecture. Okay, as you can see, very technically conservative. It won't work with NASA unless it is technically conservative. Okay, it's got to work. Those guys have got to do the mission. I don't care what anybody says. They've got problems, sure, but there's a lot of details involved in space missions, and I really don't think that various national labs and so forth, while they can contribute important ideas, can really run a space exploration initiative. I really think NASA's got to do it. So what we're trying to do is basically we've gone to NASA with this Mars Direct architecture, and we've been talking with them about it. And those that we presented it to have thought very highly of it, as a matter of fact. There are other people too. There are people with other agendas. I'm hoping, NASA is saying that they intend to narrow down the list of alternate architectures for detailed study to 2 or 3 by the end of the year. I'm hoping, and I'm campaigning, as it were, in talking with NASA people to make sure this is one of the 2, that they don't simply take minor variations off the 90-day report architecture, because I view that as a quagmire. There's too many problems with it. There's too many mutually dependent items. There was too much thinking involved in that, in trying to make the Moon and Mars dependent upon on-orbit assembly of the space station. I'm not against the space station. I'm against making systems dependent on space station that don't have to be. In engineering, you try to decouple dependencies, because if you have everything mutually dependent, it's like having an army where if one man gets shot, everybody dies. So we make them decouple and strengthen all of them, including station, by making it more technically credible to be both a zero-gravity research facility, okay, and not try to have it do all sorts of things that it's not really designed to do. And at the same time, free these other elements from dependence upon it. Okay. Now, I think that if they go for this, and I think there are plenty of good people in NASA, and I think that if they make the fight for this, and if they make this as one of the clear alternatives, and they'll modify these designs. These are not drop-dead designs that simply must be this way. But there are certain main features of the overall architecture, the overall thought plane, which you can then iterate off of, okay? If they take that and then modify it according to their own insights, but if they take that as their point of departure, I think they can come up with an SEI architecture which is sellable on Capitol Hill, because it won't be $400 billion, and you won't have to wait 30 years to achieve the major objectives of the mission. It can be realistic in cost and in schedule. And if they can do that, I think they'll have picked up a winner. If they don't do that, it's pretty tough, because I don't think it would really work to bludgeon them. I think fundamentally it wouldn't work to get into one of these things where they're always fighting with the Air Force over, shuttle C, ALS, drop dead. Okay. But I really think that's what's essential as far as the people here, in your discussion with people, is that you do not stand for the statement that will be made, because we're going to get this out, okay? I'd like to get it out in Ad Astra, talk to Aerospace America, other publications, and eventually if it gets published there, we can probably get it into the regular papers too. But the understanding must get out that SEI doesn't have to be $400 billion, and we don't have to invoke any incredible technologies or magic or anything. We can stay within the realm of things that are doable today with just a certain amount of hardware development. We can do it within a reasonable time. It can be 99, or, if the bureaucracy slows things down too much, it might go to 2003. But technically, there aren't any tall poles. It's a near-term proposition, and it's just a question of getting going. And I think if people go out with that understanding, and when you do encounter the press, or you do encounter people that you're arguing with, you let them know that you're wrong. It ain't $400 billion. And it can even, pay for itself after a reasonable amount of time with resource exploitation, but even when it's still all overhead, it's still not beyond the technical means of the U.S. alone or in concert with other nations. I'm not a politician, I'm not going to make that decision. But we can do it. Yes?
Word of caution. I've seen how government operates, and it's critical that you get the ear of the president in this effort. I know you have to go to NASA and give the presentation to NASA, but you have to get the president as well, and not through NASA.
Well, no, I want to take this. I'll take you next, Ed.
There's several corporations in Washington which are lobbying for SEI currently. McDonnell Douglas, Rockwell, and Lockheed come to mind. But Martin Marietta isn't one of them. I was wondering what you could do about that.
That surprises me, but I could ask people about why that's the case. But I think we decided, frankly, when we saw the 90-day report, it was our evaluation of it is that it wouldn't sell. Because we looked at it and we came in advance with the same conclusion that the Space Council came of it, that it wasn't a practical architecture, and that we had to generate our own path. We set up a group to generate our own scenario for Mars, and here was the ground rule. Design the best mission. Don't try to design a mission doing it in the way that these guys at Marshall or these guys at Johnson or these guys at somewhere else like. Don't try to appeal to some existing institutional prejudice anywhere. Just design the mission in the best possible way and let the chips fall where they may. Okay? And that is the best way we can help NASA, by simply trying to find the answers without, endless numbers of managers and marketeers steering the study in some way that really wasn't appropriate. And I think what we have, that we've succeeded. I think we've come up with something that is fundamentally workable. And I really hope and believe that it is possible that NASA can pick up on this. And if they do, we're going to have a much stronger hand. Ed, I said
Take Ed, and then we need to close out the session. Robert's got more time. I'm sure he can stick around a little bit afterwards. Just ask the questions and answer them after we close out the session.
It's Strickland, Austin Space Frontier. Can we get this as a slideshow to accompany the tape that we can buy at from the commercial tape people, and also as a video with the graphics professionally edited into the tape of this presentation?
well, it's not available yet. Of course, there is the tape that these gentlemen have been making, as I've been talking. And we don't have this yet as a slideshow. As I said, this literally is the first truly public presentation of this material. Eventually, I think we could probably have it. And I tell you what I'll do is, when we do have it, I will let the Space Society know about it, and then you'll be able to order it through the NSS.
Let's hit it and hit it hard.
Robert, thank you very much, and you saw very clearly what the group felt with your presentation. I can't add anything to it, wouldn't try to.
Some of the national publications that are non-space oriented. I just wanted to see about getting together with you.
Well, if you want to do an interview for some of these things, I'm game. I was also thinking about writing an article myself, perhaps for Ad Astra, perhaps China Frontier.
Yeah, right. And all this, because you just don't have enough time to do all this.
Yeah, what?
I just wanted to say I think it's an absolutely wonderful idea, and I'd like to, I work in the grassroots, I'd like to support you in whatever way I can. Do you apply?
Yeah, I do.
I really wish you well with this. What, have you been talking to your folks at Martin Marietta? What's their feeling? Are they going to put some real money behind selling this?
Yeah, of course, winds can always change, but right now, our scenario development team, our Space Exploration Initiative group, is headed up by a guy who, well, he's a great guy. He's a vice president who's willing to develop original work like this. See, most of these guys that are big in companies, they say, well, what does the customer want to hear? What should we say?
I know.
Okay, and this guy, see, he's a veteran of the Viking program, and he's identified with that all his life, and he did not want to see Mars in 2020, 2030, it was bullshit, okay? He's also a veteran of organization you may have heard of. It's legendary in the aerospace industry, called the Lockheed Skunk Works. And the Lockheed Skunk Works was an outfit. I'm running kind of low here, folks. Look, anybody who wants to can reach me just by calling up Martin Marietta in Denver and asking for my number from the switchboard. If you want my address, it's P.O. Box 179, Robert Zubrin, Martin Marietta, P.O. Box 179, Denver, Colorado, 80201. I'm just almost out.
I'm going to introduce you.
What's groundbreaking like Mars?
Parents ran away.
Well, thanks. Good.
This one has mine and my brother's home address.
Okay, good. Now you say, what is the aerobraking like in Mars? Well, this is all minimum energy aerobraking. We're not doing any high energy aerobraking. And our entry velocity at Mars is about 6 kilometers a second. Compares to 8 at Earth with a shuttle, to say nothing of 11 at Earth coming back from the moon. Okay.
Still height of the air.
Other questions?
I'm Audrey Robbins, Please come forward.
Right.
We have a space forum every year, and we'd love to have you as speakers.
Okay, when is the forum?
It'll be February 11th in 1991.
Okay, now you're obviously here with Eric.
Yes,
Okay.
I'm taking over as president during his graduation.
Okay, well look, number one, I'd be pleased to go speak there. Number two, you got my number, it's on the card, Eric has. And call me up a little later and we can talk more about it and what I would talk about and all that sort of thing. Okay? All right.
Good luck.
Bob, I'm presenting a bunch of stuff at the National Space Council on June 18th, and then I'm presenting stuff to the High Frontier Group, including General Graham on the 19th. And what I would like to do, Rockwell yesterday, Ron Jones just gave me a bunch of stuff to also present from Rockwell.
You're presenting to the Space Council?
I've got an appointment with the National Space Council June 18th. If you want me to take a Xerox set of your documents and present it in person to them, make sure that it's on their desk and that they're thinking about it, and I'll give a hip hip hooray to the whole entire thing. You know, I'd love to be able to present your stuff too.
I prefer that you didn't. The reason is this, because we're going to do it ourselves.
Okay, well, I just thought I'd let you know
Okay.
so that you had the opportunity to,
All right.
because if you don't have those lines of communication open, if you need phone numbers, if you need names, I already got that too.
Right.
Okay?
Mueller knows those guys on the Space Council.
Okay.
I mean, he's a vice president at Martin. This thing is we want to handle this in a very...
I understand, and it's just you had noted that you didn't have those lines of communication open. If nothing else, I want to offer you the phone numbers and names and all that.
Well, you can give me the phone numbers and stuff, but don't present this yourself to the Space Council. We'll present it ourselves.
Excellent.
Okay, because we know a lot of the details of the analysis that stand behind the architecture. We can answer the tough
all I was going
questions.
to do was just hand Xeroxes.
Okay.
But at the same time, I will, very good. We'll be talking about that.
Sure. Okay.
What's your address?
Robert Zubrin, Martin Marietta Astronautics, P.O. Box 179, Denver, Colorado 80201. If you want to add mail stop DC, like Dog Cat 5060, after my name. It's not really essential. There it is.
DC?
Yeah, Deer Creek, Dog Cat.
The plane that was flying on, was it Titan?
Yeah.
What's the weight on that?
8 tons.
8 ton?
Titan's really beautiful for planes like that. Escape velocity is Mach 6.
You said it was 16G?
17.
17? Okay. Yeah.
4 atmospheric densities, only 1.5 atmospheric pressure there.
Okay.
It's an interesting environment.
Yep, you got it. Sooner than you think.
Very encouraging.
Have you already spoken?
Yeah, well, unless they screw up and turn around in time, and this is going to be pretty fast. This stuff was being closely held until very recently. And we decided to go public. We're going to present it at Case for Mars next.
Why was it in analog?
Because at that time, we were still keeping it to ourselves.
You were keeping it to yourself, so you put it in analog?
No. The Nymph is in analog. The Mars Direct stuff, which is the most politically important stuff right now.
That is
Okay, was withheld for reasons which I think you can understand. But which at this point we've decided to put it out there so people can talk about it, look at it, debate it, find improvements in it. And in no case let it be buried in silence. Nice meeting you.
The power supply on the surface for the refueling. If a nuclear reactor becomes a problem, say you could go down to solar, how big an array would that be?
You mean if the nuclear reactor becomes a problem?
Politically.
Politically, it's the surface solar energy on Mars is about 180 watts per square meter. Okay, and then I think, well, if it's a fixed array, though, we're playing it simple. We're not trying to make the sun. We're just laying out max on the ground, which would be more suitable for culture. So we'll call it 60. Let's say we have, let's be a little optimistic here, and let's say we have a 15% conversion efficiency of having 10 watts per square meter of electricity, and we need 60 kilowatts.
It's about 7,000 square meters.
No. Yes. That's right. That's what it is. It's fairly large. You might be able to get by with dynamic isotope power sources, but that gives you almost like a... What?
I mean, I don't think you can get more than like 45% that's going to have a quarter of this.
Solar's a problem. I really think we need nuclear to do this mission right. It's marginal. Now, we will go with a few solar panels with the HAB, so if they land away from the reactor, they have their own power supply, and also so they have life support power if we want to shut the reactor off. The reactor is only mission critical for the propellant production operation. After that, our power needs go way down, and we could use solar. So in principle, we could turn the reactor off and go all solar after that once the propellant is made. But on the other hand, it's not. We could run the reactor, say, at 20% power. See, an SP100, just use that as an example, since that's coming along now. It can generate 100 kilowatts for about a 7-year lifetime. it could generate 20 kilowatts for a 35-year lifetime. Okay, so that's a pretty good lifetime. And to have 20 kilowatts at our base, that's a pretty power-rich environment. It's more than we need. We could do a fair amount of resource processing, especially for the smaller amounts of power we might need, say, to make propellant for the ground vehicles. It's only for this thing at the beginning where we're making a massive amount of propellant for a Earth return vehicle that we need that much power.
I'm still thinking how you can get around that because I'm paranoid about the anti-nuclear lobby. Could you shift it instead of having the manned mission be the next window, the one after that, and that would give you years of low energy silicon?
I suppose so, but
real stretch out
I'm not. I'm scared of the environmentalists. I'm a student of
Zubrin, you did magnificent job.
But
We have to find some way to get that enthusiasm into the staffs. Have you briefed any of the congressional staffs, not the senators and congressmen, the staff?
yeah, they did. Tiger,
Well, Tiger is not in a position to help you because he's with a minor congressman who's not on any of the important committees. I'm specific. He can help, of course.
it's done to be very fast. It's also thermal
entree,
which I think is
but you need to talk to the staff of the key committees.
Yeah.
On both sides of it. And,
well, I think at a certain point we're going to want to do that.
But the thing is, it's about,
our approach, we're going to try to live it through this system first.
let me just tell you that I was on the Senate
Right, I met you with JP.
yeah, and I know how these things work, okay? And if you can get some of the key staff
he belongs to this camera, I belong to the camera over there.
and for the time expended on giving this message, be like 400 people in this room, that's a highly efficient way to do it, instead of just talking to one or two people. But if you can get to the Senate and House staff people on the committees, you can have an enormously greater leverage of your time and efforts, because your presentation, as the actor has sold itself.
Now you were masses 6 months or so. You were involved with Ben Johnson.
Yes.
And are you still politically connected on the Hill?
No, I retired from the Hill in '77, and since that time I've done a few things like inventing the Student Shuttle Project and being executive director of the NSS and getting the mergers done and a few other things. But I don't have too many connections on the Hill anymore. But Laurie does. Mark Hopkins. So does Ted Littman, who's a volunteer lobbyist for us now.
Well, one thing they can do is they can take the video and they can show it to somebody. Show the code.
Can I get you to sign this with me? And then there's a grid version structure, just so you can tell what they're using.
This is a different aspect.
Oh, it is? That's about 20 meters. There's two separate. They're using thermocouples.
In any case, I just simply wanted you to understand the leverage that you can get by making these presentations to the staff, the committees that really do the work. Those people are extraordinarily important.
If you guarantee everything that we just did was technology, went to Washington was get to the staff. But
Who did you talk to?
I think
Well,
when
and I worked, I was on to that for many years.
How large is the actual?
The actual launch of the it's on the
hundreds of kilograms.
Daniel James, in the middle of this was James.
I don't know when you.
Marshall,
As a matter of fact,
one or two people I don't know total mass. But we're going to present this next week in case tomorrow.
31 years.
It's
100 kilowatts in the capital, so...
10 days.
I know he's going to be
I'm not leaving just yet, but I will later.
He's under our
Now, you've been following the NASA mission archaeologists and involved with our folks. Not really, no. But I know they know you saw it, and especially, I'm old and now, and he'll think it shoots out 5 or 6 months.
It's designed so basically you can launch it on a shuttle without taking it to the base. So it's still directly from the base goes down.
That's what the
GE would have more on this. The space and power systems.
There's something new here that Martin has. Have a lot of stuff on this. We're anxious to have a traffic system. We don't want to be like a 7-year one. We don't want to feel for a position where we're helping Congress.
One of the reasons they went to the nice rate is it's faster burning.
So they can use it. So, frankly, I think this book
It
is much
effectively lets them get more power out.
Mars. It has more short Mars than Mars.
I don't remember the details, but that's why they did that instead of...
Okay.
But anyway,
Should be fairly close to carbon.
and
So
I really want to do everything I can to encourage NASA to make this their own. Now look, right now, I mean, it looks like anything else. We've done this with a small team of people. This has to be subjected to scrutiny by much larger teams of people with much more detailed analytical tools. It has to be made into a rather large-scale item of study. But I think we've established a convincing case. We have not a fair amount of technical detail beyond what I showed. I just wanted to give the main strategy plan and flaws so people can see how it works and why fundamentally it is a simple approach.
Yell, especially on the technical stuff, so you can help you on the solid stuff.
Okay.
Especially with the tie-in there.
Okay, so you have data on energy and everything?
Oh, yes. Tech specs front to back. Royce will tell you that.
If you can, did you take down my address and stuff?
No, I didn't. Do you have a card nearby?
I'm almost out. It's
Is he making notes about...
Robert Zubrin, Martin Marietta Astronautics, P.O. Box 17, P.O. Box, okay, mail stop DC as in dog cat, 5060, okay. Robert Zubrin, mail stop DC 5060, Martin Marietta Astronautics, P.O. Box 179, Denver, Colorado, 80201, that's good. Okay?
80201.
Yeah, you got it.
Get in with Dale Fitz.
Can I take you to lunch? We can go off and talk about putting
Yeah.
this in that Astra.
Right, and Charles Walker also wanted to talk to me, and maybe we could go together.
Great.
Okay, so why don't we just hang around?
Is there going to be a tour? I'm going up to Keys for Mars conference. Is there going to be a tour Mars?
I don't know. I haven't heard of it yet.
That's just going to be professional people and talks, right?
Yeah, some advocates, but there is the political track there. But it is a more technical conference than this one. But not only technical, there is still an advocacy track there.
I want to meet some of the people involved there. I'd like to get access to
Question about the long range on Mars when you have large populations. For instance, Professor O'Neill and others point out planetary surfaces tend to be energy poor. You know, they're plenty of minerals but low in energy. Do you envisage SPS, or what energy source is big enough to support a large population?
I would just have nuclear reactors.
But then they would have to have a whole nuclear infrastructure.
Well, see, reactors are tremendously energy dense. In other words, the amount of power you can generate for an extended period of time with a reactor, I mean, put it this way, a submarine reactor generates about 100 megawatts, and it can go about 3 years without refueling. And it's not that big an item, okay?
So
if you ship that to Mars,
Is that correct?
that is absolutely correct.
Okay.
Okay.
Appreciate it.
Okay,
Thanks.
but we don't need 100 megawatts, typically. Let's say we might need 5 megawatts, so that's 20 times 3, that's a 60-year lifetime before it would have to be refueled. So, which is as long, you know.
5 megawatts in 60 years is enough time to figure out how to do something else in any case.
Right. Now, the fact of the matter is there's probably heavy elements on Mars, and by 60 years, with a serious colonization underway, we'll probably have the infrastructure required to produce uranium fuel at Mars, or maybe we'll do fusion by then. I don't know, and maybe even a solar power satellite. But what I'm saying is that initially the power needs on the Martian surface can be adequately supplied by nuclear power plants, initially for bases and later for towns.
At low latitude, the regolith is probably, to a certain depth, fully dehydrated and spent reactors could simply be buried because there's no water
There's
table
no
to worry
transport,
about.
exactly.
Deeper down there's ice and probably hydrosphere, and there's ice probably right at the surface at mid to high latitudes.
Right, but what you're saying is exactly to the point. There is no transport mechanism of any consequence in mid-latitudes at Mars. So that radioactive disposal becomes very straightforward.
What kind of a reactor would you think?
Well, there's a number of choices. The simplest alternative would be to just use the SB-100 because there's a program in place to develop it right now. It's not necessarily the optimal reactor, but there it is.
What is it? It's an experimental Energy Department of Defense joint thing. It's an experimental 100 kilowatt reactor. It uses a thermocouple
What kind of fuel?
uranium nitrate.
Nitride.
Nitride?
I got a question, sir.
Yeah.
Could you come to my town and give me
Nitride is kind of
what you give?
uranium's
The thing is,
uranium and
80% of the population are
So they're
nuclear
doing it to get some improvements.
engineers, chemical engineers, safety engineers. That would be a place for you.
I had the wrong
audience did you
nitrogen
put together?
compound anyway.
That kind of thing.
How big?
Oh, about 1,000, 2,000.
1,000 people?
Oh yeah, very easy.
Are there 1,000 people in Idaho Falls?
I had an exhibit here. I had an exhibit which I had a space exhibit there just a month ago. And I had over 1,500 actual photographs from the universal display. And I had 800 engineers showing up on my one-man exhibit.
Okay. My answer to your question in a word is yes. I think I can do it. We'd have to arrange when it can be done, stuff like that. But I think I can.
About any time what suits you.
Okay, you have a way to contact me.
Yeah, I got the thing now.
Okay, and we can be in touch on it. And sure, I'm anxious to spread the message. I mean, I'm an engineer, but I'm a space activist like
you
everybody else.
cannot believe there would be the place for you.
We may be able to get, if you're available at some point, we might be able to get Harlan Smith, the University of Texas at Austin, he was head of the astronomy department there, to invite you down.
Oh, that'd be fun. He knows me a little bit. We've talked in the past, and not about the latest material. We've talked about the NIMP and nuclear rocketry.
I have another question just before I go. What would be the expenses?
Well, as I said
How
in the
much
talk,
would you
I
allow?
don't really know. I mean,
Just a guess.
the range of guesses I've gotten are between $20 and $100 billion to establish a human presence on both the Moon and Mars.
No.
of some significance.
You misunderstood.
Oh, to go to Idaho Falls.
Yes, that's much cheaper.
Hey, he'll fund your
Between
program.
20 and 100
I should have kept going. I should have let you kept going. That would be a good profit, boys.
Good way to make some money.
Good way to get the thing on.
Well,
I
I
guess
think
I have to take care of the airplane ticket and.
I don't think you'd have to. I think we could talk about that as a last resort, but I think that if you could advance an invitation and make it clear that there was an audience there, that in other words, that you were going to organize a serious audience, I think I could run by our PR department to send me out there and it wouldn't cost you.
There.
Okay, in other words, they would take care of my expense, you would have to take care of your expenses, that sort of thing. So but you know, if you were to send me a letter saying, look, I heard you speak here, I really would like to have you come to speak to my group here. We ordinarily get 150 people, and this and that and the other thing. I think it'd be very valuable. Why don't you come? I could show that to our PR department. They would say, sure. It's a little trip up to Idaho Falls anyway. And
Little trip, 1,000 miles.
well, from Denver.
Oh, from Denver. No problem.
That's where I live.
Oh, I see. I see.
Okay, so in other words, I think it can be done, and I don't think you have to pay my airfare. If they want to send me, they'll pay the $200 plane ticket.
While people are throwing out places where they'd like you to speak, I'd like to throw out UC Berkeley too.
Okay.
No, a couple of things. One, I have a feeling you're going to do a lot more PR
So I
in the next few
will
months
get in
than
contact with you.
Yeah.
Okay?
Okay.
Yeah.
Congratulations for the best speech I ever heard.
Thanks.
You talk like a Swiss. Guess why? Guess why? I'll give you just a short hint. I grew up there. I'm here since 35 years. But as I grew up in school, I heard the history of Switzerland. It's the oldest democratic ruling system since 1292. And in their history, they won every battle. Sometimes there were once against 2, against 5, against 10, against 20.
Okay.
So the main reason why they won the battles, they never ask if we win. They only did one thing, we battle. And that's how they won the battle.
Okay, I understand.
Couple items. This quickie article that was in the Columnist is a discussion of the NASA and Lawrence Livermore plans, and we have our own proposals for an architecture compared with those two proposals. It's more reusable, but completely reusable or more complicated than yours. There may be some useful ideas in there.
I ask you to do me one favor. You can make a glass of water.
One quick suggestion.
Joining you literally. I would like to suggest that you bring every business card you own to the Case for Mars conference.
All right, yeah.
I was saying before, as we discussed the other night, we don't work in a political vacuum. And even though there's no technological showstoppers here, going up before Congress and saying the N word at any stage of this is going to create problems.
Yeah, but see, my fundamental feeling about it is the following. Look, on Earth, okay, we have as serious power sources fossil fuels, hydroelectric power, and nuclear. Okay, those are hydroelectric. Oh, here's the water.
Yes,
Thank
there's
you.
the hydraulic.
Hydraulic.
How much energy do you produce pouring it down your esophagus?
That's about a foot drop.
Somebody wrote a story about it.
Okay. Now, on Earth, we can survive without any electricity. People did it for a long time. Okay. On the Moon, on Mars, electricity is life critical. You can't live without it, and certainly you can't prosper without it. There's massive, all sorts of resource processing things. There's some you can do with thermal energy supplies, but even so, that's energy. Now, solar energy. There's certain things you can do with solar energy, especially on the Moon, but fundamentally, it's a feeble energy supply relative to what we can generate with nuclear. And if we're going to get past the stage of camping out, okay, and get to the stage of actually having a spacefaring civilization, we have to cut that thing. We cannot have, we can do missions to the Moon without nuclear power, and we might even be able to do a mission to Mars without nuclear power, though it gets hard. But we are not going to have a civilization on Mars or even a substantial base on Mars without nuclear power. And I really don't think we'll have much on the Moon without nuclear power when you get right down to it. There's just too many problems with an all-solar approach. And so that if we want to do stuff beyond the minimum, we have to deal with it. Now, I'll tell you something. Okay. I wrote an article on the NIM for Nuclear Forum for Carl Sagan's magazine, The Planetary Report. Now, Carl Sagan's not especially pro-nuclear guy, okay? But I wrote how you can do all these great space missions with NIMS, okay, to Mars and Titan and hop around. He said it was a terrific article. They're running it next month, okay? All right? And that's because it does something that he wants to do. Now, this guy won't blink if they shut down 4 commercial nuclear power plants here on Earth, because as far as he's concerned, it can be generated in 6 different ways, okay? But because it does something that he wants to do. Now, I'm convinced, and I think everybody here is really convinced, that fundamentally the American people want to create a spacefaring civilization, that they have just been inadequately organized to vocalize that adequately, that people really do believe in progress, okay? That the Apollo program was cut short by the short-sightedness of the politicians, not because the American people wanted to stop going into space. They had no voice at that time. Organizations like this really didn't exist at that time in any serious way. And when the politicians lost their interest, there was no one there to prop up the program, and it collapsed. This time around, I think the SEI has come bottom up. It has come through a decade and more of organizing by this and related organizations. And the idea has percolated up from the grassroots, from this, from the L5, from the Case for Mars, and so on, until it has materialized into an SEI. It's not just something that dropped from the sky with George Bush. And so I think we've got a chance of pulling this off. And if we pull it off, we need to insist on getting the things that are needed to carry it forward. And one of those is nuclear power. Now, I was the transportation consultant to NASA's Exploration Technology Working Group last year. And I and a couple of other people, you may know Stan Borowski,
Yeah.
we managed to get nuclear thermal rocketry categorized as a Category 1 technology, which is why you heard J.R. Thompson and these NASA folks at this conference all of a sudden talking about nuclear propulsion, where a year ago they would not have talked about it. And if someone from the floor had asked, why aren't we talking about nuclear propulsion, they would say, look at that, doesn't work. So now all of a sudden, the party line is nuclear propulsion is important, and NASA is committed to at least taking the first steps to redevelop it. Okay? Surface nuclear power is also very important, possibly even more important. I think, you know, while it is useful to have fallback positions, such as an all-solar scenario, I don't want to cut and run before the battle is, because we really need to do this. Now, the other thing that I think you may have observed about this whole scenario is that it is predicated on in situ resource utilization right from the start. Okay, to me, it's axiomatic. I think most people here understand that. With the moon, it's a little harder to have an initial lunar mission use in situ because of the fact that you're breaking down rocks. On Mars, you don't have that problem. You're dealing with a fluid medium right from the word go, and we can develop and test out infinitely all sorts of automated chemical processing systems. This is not really a robotic situation. It's just, but even so, of course, the moon eventually we do move into that. But to think about the problem in those ways, to think about the scenario using the in situ resource utilization and leveraging the in situ resource utilization to the max, not just integrating it within a mission architecture that was designed around non-resource utilization. You know you're going to do resource utilization even on the moon, okay? So you design your architecture to use resource utilization, and even on your lunar mission you might think a small inefficiency on the first couple of missions. It's not a big deal because we're designing to actually interact with the space environment and not try to pretend we're not in space. You know, we're not trying to be the accidental tourist who goes to Paris and locks himself in the hotel room and watches American videotapes. Okay, you go to Mars, you interact with the Martian environment, otherwise you don't go.
As far as the ore development on Mars, which are deep exploration and colonization, since the planet probably did not have long-term sustained geochemical cycling, it probably did not develop things like massive carbonate bodies. On Earth, many of the ore deposits result from such things as volcanic or hydrothermal interaction with massive sedimentary bodies. Mars simply will not have some major ore types that Earth has. It will almost certainly have much better and more diverse types of ores than the Moon has. If you want ore materials in the solar system, in all probability, go to that bubbling cauldron called Io. It's in a hell of a radiation environment, but oh God, is it going to have spectacular ore deposits.
Actually, he's already solved the radiation problem there. His magnetic sail idea works very well for radiation shielding of a magnetosphere.
Yeah, that probably might work. But anyway, on
10 to 20 MeV radiation?
Yeah.
Excuse me, I got one question. It's a little off the topic, but it's just as important. You've got great ideas here and everything, and we need to get them out. Where are you in? Is this in a paper that's ready to go?
It's an analog.
well, some of it's in analog. Some of the stuff about the Nymph and Titan is an analog magazine, March 90 issue. If these guys don't screw us over, in July we'll have the Mars Direct stuff in Aerospace America. And the colonization, I have a fraction of it, the Ad Astra from a month ago. Yeah.
What I'm looking for is a packet that, can start getting, number one, are you ready to circulate your stuff up around on the hill to get into the Space Council?
Yeah, now that you've released it, is there the ability to get a paper together for, not to be handed to other people, but just for
your own education?
Your own education.
Well, the other thing is...
What I recommend is this. Look, do you know where to get Aerospace America?
No, but I can find out.
Okay. look for the July issue. We'll have a paper in there unless something bad happens. And then you can obviously photocopy that and hand it out, as everywhere and anywhere and all over the place. That's close enough, I think, that it will do it. When you take a look at the July Aerospace America, and if by some bad thing it is not there, write me and I'll send you something and that you can use.
You expect to publish
We expect to
this
publish
architecture piece, basically, in Aerospace America?
Yeah, in July.
Okay, great.
That's what they're promising us now. We had a painting produced. You know that picture of the Mars base with the HAB and the ERV and stuff? We've had a painting done of that now. So that's nice. And then we have CAD drawings of the various vehicles, and we have this computer software and stuff where you can turn CAD drawings into solid CADs that look like real metal objects and everything. We have some of them. So, yeah, I'm really crossing my fingers that these guys at AA come through because that magazine penetrates into the required political layers. That's why I wanted to publish there first.
We distribute copies to staff and to members, all members on the Hill, Space Council, all staff and members, the White House.
Well, I want to...
Well, and I want to introduce you, Robert, to Kate McMains.
Hi, we spoke many times.
Yeah.
Glad to finally meet you.
Sure.
And I'm sure I know these guys are already on your dance card to talk to you about Ad Astra.
Right.
For some future work here.
Yeah. Why don't we get together now?
Let's do that.
And why don't we have to break it off? Look, I really...
Best two talks that I've heard.
We're all pulling for
Think
you.
about Apple, too.
Okay.
We're all pulling for you.
All right.
One last question. At Case for Mars, you're going to be going into more detail?
Well, actually, probably less because we have time limitations, though we'll be around to answer questions. Baker, my collaborator on this, will present the near-term stuff, and I'll present the hard-term stuff there. Though there's going to be a workshop on architecture at Space for Mars. We'll be there to mix it up with people who have other ideas, and eventually come out with a kind of a Case for Mars architecture. But we believe that this is an excellent point of departure, though naturally we're interested in possible ways to improve it. But we think it is the correct line of thought, as it were.
Yeah.
Okay.
Yeah, and I'll get back with you too.
Right. Your name once again, Pat Jackson. Okay.
Pat, did you sign a release? For you guys?
This isn't my camera, but
Okay.
they did have somebody. I've run out of my writing cards, and this is my little prospector team card. So.
Great.
It's still you, right?
Yeah, still me. Yes, still getting it.
Why don't we sit down some more?
Hey, just like
We keep going.
Thank you.